So I'm Aghasi Tavadyan. My talk is The Dangers of Mindless Forecasting, and my talk can be summarized in a joke. So back in the day when I was starting to do data science, I thought that I was scary data science, a wizardry, and it required a PhD, and computer vision was magic. Now it's all boiled down just in 5 lines of code in Python. And this is a problem because AI is now a buzzword, and AI is being commercialized, and big companies say you need bigger, better models that took a lot of time to compute, to calculate the highest metrics, and use our platform and do it in 2 or 3 seconds and give us the money. So this is the problem we face, because I want you to understand that there should be a paradigm shift, because you don't always need the models that have the biggest, highest, best metrics, because those models don't apply to the real world. So let's have a quiz. Find the connection between those pictures. First of all, points to those, extra point to those who can tell me what the first picture is. This is the density function for normal distribution, the first picture. The second, I hope you know, Kim Kardashian, okay. The third picture is a mock-up of some buildings. And the fourth picture is a neural net. So are there some ideas? All right? All right, yes. The connection between those pictures, that those are all models. Besides the second one, because strictly speaking, the second one isn't a scientific model. A person, just an Instagram model, okay? But everything we do, everything we try to understand, everything is a model. Even our understanding of a world is incomplete model of the world. And each has his own incomplete understanding of the world. So, and mathematics has a beauty. Mathematics is the nearest thing that can describe the world, okay? And farther from the mathematics, the more noisier are the models. So mathematics, rightly viewed, possess not only truth, but supreme beauty, as quoted by Bernard Russell. And I wanted to show you a video clip here, because we have the reality, some probability, and models. Those things are models. These are the reality we want to understand. We want to predict. Everything is a model. Even we can go, and when modeling, we can go from simple to most complex. For example, if we want to model an airplane, let's say we have $1 million airplane, we want to understand, to model, we can do it in quite a few different ways. For example, I can take a piece of paper. This is the thing I want to model. This is my basis. And fold it in a couple of ways. Let's fold it in. Okay. Fold it in. All right. Couple of folds. And we have a paper airplane. And we can launch it and do some calculations, and based on these models, find some truth. But this is a simple model, because you saw how quickly I made that model, how easy it is to analyze it. And when we are in that extreme, it'll give us a lot of errors, because it doesn't represent the world truly, fully. And on the other end, we can have extremely hard models that try to include and describe everything imaginable. But those models are problematic as well, and they can give results that are harder to explain, harder to understand, and results that can be very very far from truth. So we have two extremes. All right, let's go. So there are some cycles. You have seen the modeling cycles. It doesn't mean, it doesn't matter what kind of cycle we use. What means is that it is a cycle, because modeling is not a linear thing. You come from one point, analyze the data, and have the model. It doesn't end there. It's a cycle. And there is a question, why is it a cycle? Why the representation of modeling always follows a cycle? That's a question. And there are some answers I want to think about. Usually, I let the auditory to answer this question, but this is not that format. So, firstly, the thing we want to model constantly may change. Even when modeling and having answer, our answers to the model may change the system. For example, we are predicting the stock market, and our predictions in the future will affect the stock market. So thus, we must start the predictions anew because the system have changed. Secondly, we may start with simpler models to understand how the things work. And at the end of the first iteration, when we understood the simpler model, the paper airplane, we can start modeling with wood and so on before we are an expert and can do harder models. And thirdly, those two things. And all right, let's, okay. And we'll go for this. Life is not a Kegel championship. Like this is our old friend, the Magpie, who chatters the truth. So life is not a Kegel championship. Most often, models with inferior metrics are better in the real world. So I hope you know the story that there was a champion. There was a championship on Amazon to code the best model that can describe everything. So the most complex model was used with 30 different models that were combined into each other, and it gave a lot of good results. So it surpassed all the expectation. But this model was so hard to implement, so hard to code, and so expensive that Amazon refused to use it. Because, and right now, there is commercialization of models. And everybody says, use our, like, I'll give an analogy to the kitchen. Like, you can cook a breakfast with simple pan. But everybody says, use our new, commercial oven 5000. The latest, it has the latest GPUs that costs a lot to prepare any meal. But that's like throwing a big, huge, expensive solutions to a problem that can be done in less expenses. So that's why I want to shift your paradigm, because models that have the highest metrics aren't always the best in the real world. Sometimes models that are more explainable are easier to understand and better. To illustrate this, let's follow a Kegel championship that is famous, predicting Titanic survivors. Okay, Titanic survivors. So we have a simple classification tree for Titanic, okay? That has 4 branches. Some may call this a faster frugal tree, because you can do this without using a computer, just following some lines and coming to conclusion, okay? So first, it asks, is the title Mr. or Mrs.? Yes, then there is a 16% survival chance. No, the second question. Third class, then yes, okay, then 60% of survival. Everybody can understand this model, okay? This is a simple model, okay. And when viewed from metrics, okay, a lot of people were doing classification, you only use Aghasi curves. Aghasi curves were developed in the Second World War and have an archaic name which I don't like so receiver operator something. It's just we care about the area under the curve, which when higher, then the model is better. Lower, model is worse. Everybody is speaking about that. No, but like a few people, only a few people speak about accuracy, sensitivity, specificity when doing models. Because when modeling, when doing classification, sometimes maybe sensitivity is a better metric. Maybe specificity is a better metric to use to understand which model is better. Okay, so, and I hope you do know that we must divide our data into testing and training sets. I won't go into why it should do, but strictly speaking, when we are learning for the exam, we don't want the same questions we learned on to be on the exam. We want the exam have the different questions. So we are dividing into training and testing sets. So to train and to test our model. So to test on a data that the training, the model hasn't seen yet. Okay? So on the spot cases, we have the accuracy. So the right predictions divided to the whole is 80 to 81% around. There are no strict numbers, okay? Sensitivity is around 75, 78%, and specificity, sensitivity is right cases divided to prediction, and specificity wrong cases divided to the prediction, okay? Those are, we should to know. This is our model. It does good. It is good. And this is the Aghasi curve of the model with different thresholds. We can change the threshold to have different sensitivity with sensitivity and specificity threshold. Those are two combined. We can have high sensitivity but low specificity and vice versa. So imagine you want to do track texting or COVID texting. You want to understand how much you want to have false positives and how much you should have false negatives. The lower the false negative, the higher the false positive and vice versa. This is the threshold we care about. So, and we can do an overfitted classification tree. Like overfitted models learn from, like we can overfit a model on testing, on training data, and it will answer, like, can answer 100% of cases of the training set, but it will fail on new data. This is a problem. Okay, this is an overfitted classification tree. But as I told, simpler models sometimes are better. And let's see how this simple model, the classification tree, which you can understand, you can do by hand, not using a computer, compares to more expensive and more harder models. So this is an average, so average estimation. So everybody has 39% of chance of surviving. So this is our benchmark. In this case, area under the curve is 50%. Accuracy is 64%, so it's fine. And barrier score, which I will not go into, which is the lower, it's the sum of the errors, okay, squared errors. The lower, the better, okay? It's fine. This is a bit like a harder model. So all this is a simpler model as well. All females silver, all males do not. So it has higher accuracy. But we care about simple classification tree. So from all the models we have, so we have overfitted classification tree, logistic regression, random forest, support vector machine, natural networks, average neutral neighbor, nearest neighbor, so a lot of different models. And random forest, neutral neighbors are harder to compute, are harder to explain. In all of these questions, the accuracy is higher on simple classification tree. So using just classification tree, we can derive the same answer. And what about the area and the curve? So when using this matrix, random forest does better. And this kind of the forest models, XGBoost random forest, have that problem. They maximize the metrics. They have higher metrics. But is this good in the real world? You must ask. Will this, there are some problems, I'll talk about those problems as well. And Barrier Scores has the best simple classification tree. Besides, those metrics aren't strict. They have a probability field. They have an error. And within the error of the best metric, let's see ROC curve, may lie the simple classification model. So you should ask, why should I use a harder compute model when this number may lie inside this value, okay, the error of this value. So the modeling is a balance, okay, it is an art. Not only just ready-made, and put your ingredients here and you'll give the results. It's preparation, it's cooking, it's art. And from one side, you must understand that your model must be as easy to understand, implement as possible. From the other side, as hard to use the most fresh ingredients that describe the whole system that you need. So it's a balancing act. Because there are some systems that have a lot of variables. Should you use all of those variables? No. You must understand which variables are more important to use. Okay, so extra point to those who know what this dinosaur represents. Show hands who have seen this dinosaur. Only one. All right, couple of guys. But let's speak about the pitfalls of forecasting. First of all, the game's rules are constantly changing, so lack of robustness. So in real life, the game rules always change. So the data represented 1 year ago, 6 months ago, the causal links aren't the same that are now. For example, if you are trying to model, to forecast a football match, so everything is constantly changing. The trainers are changing, the players are changing, some player may have an injury, so a lot of things are constantly changing. So the causal links that applied 2 or 3 months ago are the same that apply now. And you must understand this. I spoke about this when we are talking about the cycle. And constantly adjust your model. Or to understand this and to build a model that plays into this. For example, you are not analyzing the whole teams, but separate players. And they have their different curves of performance, separate trainers, and they have their curves of performance, and combining them into one model. For example, you might understand this. Second, small samples. This is a problem because any sample may be expensive. For example, you are doing bioengineering, and each sample takes time, takes energy, takes resources, and it is expensive. But like the world is random. If you throw a dice 10 times in a row and repeat that experiment, let's say, 1,000,000 times, there is a high possibility that two consecutive, like two concessions of throws will be the same. So they will be correlated. But is there any causality? No. Just randomly, they are correlated. Okay? So like these expensive models, random forest and neutral network, work when there are a lot of data points. When you are doing, there you have a small sample of data, you must understand that you may predict on randomness, okay? And you must do future engineering in a way that overpasses this problem. All right, I think I have exited the slide, okay. And the third one is relatable to the second one, so lots of variables. For example, when we are having the sample is expensive, okay, we may have a lot of variables. So one line of sample may have a lot of variables, and this means that when we have 40 variables and let's say our sample consists of 15 lines, there are high possibilities that there will be correlated. And the rule of thumb is that for each predicted variable, for each variable that we are predicting on, we need 40 lines of data. So when doing bioengineering, you must choose which variables are the most important, okay? And when you have only the sample of 120, when you have a sample of 120, you only must choose three variables you should predict on, because there is a high chance that this will be correlated. There will be correlation and not causation. This is important. And fourth, some variables are estimated, not measured. What this means? Okay, there are some variables in our system that inherently can be measured. They are estimated. This can be inflation. This can be on survey. How do you think, like give an answer from 0 to 10. How do you think our president is going to do this task or something like that, okay? This is an estimation. We can't be sure that this value is 100% correct. So this value has its own distribution of error, and this must be accounted as well, okay? So the time has come for shameless plugin. Okay, so but before the plugin, let's speak about different models. Okay, I'll go to Tavialcom. Okay, this is my company. Okay, and the interesting thing is that this the logo you see isn't generated by graphical interface, for example, Illustrator or Photoshop. It is generated by a function. So it's a mathematical function inside the unit circle that has a changing parameter, and it dances and it changes, and we have a logo. But I want to show one of our projects that went to these pitfalls. So this is a classification that classifies around 3,000 different classes, and those are classes, so those are our customers. And we want to understand for each customers, for the day we are talking about, which items they will be interested in. Okay? So in this case, if we use random forest doesn't perform. It's a model that gives, like in my experience, one of the highest metrics in machine learning. Okay, one of the highest models in metrics in machine model. If you tune it correctly, it's very good, but it takes a lot of time to train. Moreover, if you have 3,000 or so classes, the time goes exponentially higher, okay? And it's very expensive to train. It has a very large model, and it's very hard to implement. And it has a lot of different pitfalls. For example, in my experience, like random forest doesn't provide prediction for around 20-30% of classes. So when predicting 20 or 30% of classes will not have any prediction. So they won't be shown. For example, you have a store that predicts items for each and every person. 20 or 30% of your classes or your items will be not shown at all, because random forest maximizes the metrics, and you will have higher metrics, like harder model to implement, but it will have problems in the real world. And other models may have 10% less metrics, may be 40 times, but maybe 40 times or easier to train. So the time to train will be 40 times less. They will be easier to implement and to understand. So, and they won't have problems like this. They'll give predictions to all of classes. So this is the thing you must understand. Okay, and by the way, this is a working prototype. This is this is our work I did for Blueberry Zandastors, which is the representative of those companies in Armenia, and this has sensitive data. So the names are randomized, and a lot of stuff is hidden here. Okay, so. And right, let's return. So I've spoken about my my company, and let's speak about our book. So this is the second shameless plug. So our book, Uncertainty Bands, which is a guide to predicting and regulating economic processes. So it's a la Black Swan. So it discusses the philosophy of prediction in economy, if you are interested in. It's available on Amazon. This book my father has written this book, and I had the pleasure to translate it into English. And there was like the amount of correspondence of 2 years between the publishing house was on me. So it is available on Amazon and all the major retailers. If you are interested, you can look it up. And I think that will be all from my speech, and I'll be awaiting your questions. Thank you. Are there any questions? By the way, dinosaurs, it's an interesting story. There is a ASCOM quartet as well, which about like, there is a good topic in statistics that everybody should know, that correlation doesn't imply causation, okay? Because, and vice versa. And there may be data that has the similar metrics, but in reality isn't the same. You should understand this. So, are there any questions? Okay.
Thank you for your presentation. You said that there are some features that are estimated not correct. They have their own error distribution. What to do in that case, and how to deal with that features?
All right. So we must, okay, we can do a lot. This only shows that we start with a recipe that has a built-in error inside, and this error will proceed, and small devils on the way, like each error is a small devil, may combine into a big devil. And this only shows that if you have estimations in your project, that this doesn't necessarily mean that the final metric you have will have a calculated error. The error, you must account that the error will be greater. Okay? And in a case that we have a lot of estimation, the simpler is the better. All right. Any more questions? I feel like I haven't I feel like your questions is somewhat a metric of my presentation. The more the better. So one more question. All right, then let's end this. Thank you.